Alright, so let's do exercise 2.4. Let x and y be real vectors in Rn. Prove the triangle inequality, which states that the norm of the sum of vectors x and y is less than or equal to the sum of the norms of vectors x and y. You may find the Cauchy-Schwarz inequality helpful. First, before we begin, this is a very geometrically intuitive inequality, and it's a very popular one that's used all over the place, especially in proofs. So let's go ahead and draw this. We'll go ahead and look at this drawing in R2 specifically. It's easiest to see, but in Rn, this generalizes quite nicely. So this drawing uses the usual way of visualizing the summation of vectors, which is to move one vector's tail to the head of the other vector, and we see that x plus y is now given. So the idea, and the reason this is called the triangle inequality, is that the triangle inequality is that the length of x plus the length of y has to be greater than or equal to the length of the sum, because they make a triangle. That's sort of the geometric interpretation. There will always be a greater length in the sum of the two lengths, unless there's an equality, which is the case when we have collinear x and y when they're both in the same direction. So let's go ahead and do the mathematical proof now. We begin from the property that we actually derived, or we proved, in exercise 2.3, and we'll apply that directly to this norm of x plus y, and we'll square that norm. We saw in that exercise that precedes this that the square of the norm is the equivalent of a dot product of the two vectors together. So we have x plus y being that's the vector that is normed, dot x plus y. Good. Now, taking this dot product and expanding it can be done if we use some other properties of the dot product, which are its distributivity and its commutativity. So its distributivity says that we can take x dot x plus x dot y plus y dot x plus y dot y, just as we would in a typical standard algebraic problem where there's regular multiplication of scalars. So let's go ahead and do that. We can do x Now we can use the property of the dot product that the order doesn't matter, which is also called commutativity. So the dot product commutes. You can switch x and y, which means that these two terms in the middle are identical. So we could write them as either x dot y or y dot x. Good. Now we can identify that this term and this term, dot products of vectors with themselves, as we know, are just equivalent to the norm of the vector squared. So we can make that simplification or identification. Good. The Cauchy-Schwarz inequality comes in here. So we can say so we have a term x dot y in the previous expression, so we're going to use this inequality to give us an inequality in the above expression. So we can say, therefore, returning to this term, and we were able to do this because we knew that we have equality when x dot y is equal to the magnitude of x times the magnitude of y. We know that x dot y is always going to be less than or equal to that. We now have this inequality, and we have very close to what we need, but we can take a couple additional steps. The first step is to factor. These are just scalars, right? All these norms result in scalars, so good. Finally, we can take the square root and we're done. Thanks for watching.